Hello, Poe. Welcome back. I'm Professor K. This is Antigravity Explained, Part 2. In the first video, I talked about how anti-gravity might work if you could have such a thing. And, I'd like to point out that's kind of a big if. I mean, it's just as likely that there is no anti-gravity. However, we did talk about dark energy here. If these are our galaxies, there is a force, pushing against them, accelerating and expanding our universe. And really, it is, in a sense, this anti-gravity with what it seems to show. Is it anti-gravity? Well, we don't really know. We don't know what dark energy is. But it's unlikely right now that it is anti-gravity in the sense of what we were talking about before. And I'd like to also just kind of say it, there's other unification theories out there. And I'm not trying to take away any credibility or anything that they have because, some of them are these great theories. And is one better than the other? Well, the issue is a lot of this stuff might just kind of remain theory. Because as you ask the question, how does this work? Well, you say it like this. Well, okay, then how does that work? And for each iteration of the deeper you go, each glass of water just kind of holds less and less water. And there might just be things that we will never know. It's just beyond our ability to ever know these things or understand. Now, I used, like this graviton-filled ether, as a way to describe, a way to unify these four forces. But really, that's just kind of because it gives you this more visual picture, more visual representation of what's going on. And so the thing is, is gravity just this warping of space-time? Well, we know that for every little bit of matter that's out there, with it comes some little bit of this gravity, this warping, of space-time. And we express it in a way as kind of like this force. Maybe it's a force, maybe it's, just the way, this fabric of space-time warps. But there is some amount of energy, in a sense, that can be calculated or associated with that. And it's not impossible for gravity to kind of act like a current, in a sense. Right now, there are approximately 1 trillion neutrinos that are passing right through your body every second. There's 1 trillion. There's another trillion. Okay? And most of these neutrinos, they come from our sun, and they pass right through the entire Earth and you as if the Earth wasn't even there. They just don't interact with matter. Thankfully, because if they did, they'd probably be ripping us apart. Now, I talked about, other theories out there. You can kind of see, maybe space-time is this fabric, this three-dimensional space-time with this fourth or fifth or, however many more dimensions of something that else, this higher dimension that's kind of interwoven into this fabric. And that's, something that we might not be able to reach or understand or put our finger on, but it's just, that's the nature of things. And we try to use, what we know, all of say gravity, as this, effect. And it's really comes down to a lot of the mathematics. And we express things, pretty much all things really can be expressed as a ratio. Like pressure is, pounds per square inch, or, speed is miles per hour. We just compare things the best we can, and that relationship between them, in a sense, to express, these forms of energy, like gravity. But in a sense, it still is this extra, force, or this energy that comes with stuff. And so really it's kind of like this big question we have, which is, what is energy, right? What is this? What do we mean by this? Now we're going to go down a rabbit hole here in explaining this, but don't worry, we'll climb back out. It's just kind of one of those things that, to describe in a way or whatever, we kind of just want to lay this out so you can kind of get a perspective or view on this. So that we live in 4 dimensions, 3 dimensions of space. You got length, width, height, or X, Y, and Z, however you want to look at it there. And 1 dimension of time, or when. But the thing is time is not really this 4th dimension. And just hold on, because I will explain this. And the best way for me to do that really here is to just kind of draw it out, okay? So we use a point, a single point, and as a reference or a location. There's nothing about this point. It doesn't have any dimensions. It can't be measured. It's infinitely small, however you want to look at it. It doesn't have, it's really just that place where X and Y meet. It's the idea of a location, okay? So we say a point is dimensionless. It doesn't have any dimensions, okay? So two points gives us this first dimension. Okay, so if we draw 2 points here, which is length, right, or a line. Now we can measure, say this dot that I drew. I can measure this very edge of the dot and this very edge of the dot. Those can be my 2 points, and measure the the length of that dot. But what we're really simplifying here is that these are our 2 points, and we can draw a line between them, and we can measure the length of that line. And that's our first dimension. So 3 points gives us 2 dimensions, which this as a flat point, or area, right? Did I say flat point? Flat plane. So this plane, and we'll draw this out. Here's our 3rd point here, and we can connect all 3 points with a line, and we have this flat surface, this plane, if you will, kind of like this board. And no matter how you rotate them, they all it's like this sliced layer of space, and all other points are included within that. All the other points that come with it are just kind of assumed to be included in that plane, or in that line, whatever that line is. So 4 points gives us 3 dimensions, which is length, width, and height, or volume, and also, our 3-dimensional shapes, as you will. Okay, now you need at least 4 points to get a shape, a 3-dimensional shape. You need at least 3 points to define a plane. You can have more, like I say, points, but you need at least this number, at least 2 points to have a length. Okay. So we'll draw our fourth point here, and we'll connect it to our other remaining 3 points. And there's our three-dimensional object, if you will. You got, 3 triangles kind of folded up and one on the bottom. Okay? So what does 5 points give us? Right? What is this fourth dimension? Okay? Again, the best way for me to, explain this is to just go ahead and draw it out. Now, I am writing on a 2-dimensional surface, so you'll just have to kind of understand what it is I'm doing here, but the best way I can explain this is to just kind of draw this out, if you will. Okay? So what is this, fourth dimension? If it's not time, what is it? Well, let me draw my 3-dimensional object here. I'm just going to draw a cube. Okay. And then I'm going to draw a cube. And this is the fourth dimension here. This cube here is this cube here. It's not another cube. It's the exact one. Okay? So you say, well, how can this cube here be that cube? And the only way we can understand this, this movement here, is through something we invented called time. You say, well, what happened here? Well, time happened. First, it was here. And now it is here. And time is so easy for us to grasp a hold of, this concept, this that lies purely in our minds, that we've encrypted it into our language. And we don't just have words, we have tenses of words to describe time, so much so that in our explanation here, you can see first, kind of describes, that it was the first thing to happen. It was first here. It was like this moment in time, right? Was says, well, that happened in the past. That's where it was in the past. And it is here now. These are all words just in our language that describe time, right? You could say next, previously, right? But this fourth dimension really is motion. And we invented time so that we could understand motion. Right? That's really what it kind of comes down to. Okay? Now, I don't like to, categorize things. But another way to look at this is to say, okay, well, what do we know is real? Right? This would be our physical realm. This would include things we know, like motion. Okay? Because you can see motion, you can feel motion, you can feel yourself moving. You can sense this in many different ways. But we're going to call this the conceptual realm. And this, it can be real, but it doesn't have to be. Like ideas, thoughts. Okay? Time. is just a concept. Over here you can have, birds, trees, sunlight. This stuff here has to be real. And we know that. This stuff here doesn't have to be real. Okay? Now the thing is motion is included into this 4 dimensions of space and time. So what's this stuff over here? I mean, ideas and thoughts, they're real, right? I mean, what about a feeling? Feelings are real. You can have a feeling and it can produce chemicals in your body. And you can track those chemicals and be like, hey, look, there's proof of a feeling. But yet, not every time you have a feeling about something is there a chemical change in your body. It can be, something that's hard to, track or prove that it even exists. And without that evidence over here of a feeling, how would you prove that you had a specific feeling at a specific time? Good luck on trying to prove to somebody, how you feel about something. Because the only thing they can do is take your word for it or say, or how you vocalize it and trust that that's real. Okay? But this stuff here, I mean, this has got to be like, I don't know, 5th or 6th or just something in a higher dimension in a sense, because you can have an idea or a thought seemingly out of nowhere that says, move my arm. And you just created a motion over here in your 4-dimensional space-time. Just by having this thought, this concept. And you can also have an idea that's something ridiculous, like apples are bananas. It doesn't have to make sense. It's not real. So over here, like I say, it's just one of those things. Our logic is wrapped up into our language, and our language for things is wrapped up into our own very logic. Okay, and our language and our logic is somewhat paradoxical. You can have a sentence that makes perfect sense, and this sentence is true, right? Nothing wrong with that sentence. But if I take and I just change it to false, suddenly there's a problem here, and that is, if this sentence is false, well then that would make it true. So which is it, right? So we run into a lot of these issues, if you will, with our own very logic. Our concept of time and, time travel, how we view things. And it might just be ingrained or built into us, some type of flaw that is ingrained into us, and hence our logic is flawed and paradoxical because of it, or we just can't understand things because of this. And so we rely on, a new logic, and that's mathematics. And, we try to say, okay, well, this can be proven over and over. But even our mathematics are really kind of this, conceptual thing, a lot of it. And perhaps maybe our flawed logic has seeped into it. And, you end up with infinities, or, you could even argue and say, that's why we have irrational numbers, because of our invention of, negative numbers. What is a negative number? Is there any negatives that really exist in the real world? Because if something exists, it is. It can kind of be given this positive value. And so to say something's negative would it be say it doesn't only not exist, it not exists in this, other opposite direction. Maybe our logic has kind of infiltrated some of that. And if you look at it in terms of, let's just say, if there was some, alien civilization far away and they were this super intelligent and their technology was way better than ours, you could just say, well, chances are they're just better at math. And that's why their technology and why they have this better understanding that maybe we just can't achieve just yet. Okay? So, coming back to this, motion is really kind of what we use to explain energy. Okay? Now, you can call the fourth dimension time if you like, and there's nothing wrong with that, because if you stop time, you stop all motion. So you can't really have one without the other. This is all kind of like, interlaced. It's all one thing, but yet defined separately. Okay, we say energy is, the ability to do work, or work in motion in a way, and that's what it is. Okay. Now you could do away with time, that we use as a concept in a sense, and say, well, let's say I wanted to explain a car going 36 kilometers per hour. How would I explain how fast my car is going if I didn't use some form of time? It's covering a distance over a certain amount of time. How would I explain that if I didn't have time? Well, I can give you a minute if you want, and you can, think about how you would express that. But really, you would need some other constant to compare it to. You would need, something pretty reliable, like light. In which case you could say, okay, my car is going 10 meters for every my car is traveling 10 meters for every 299,792,458 meters light travels. And that would be your constant, right? Because that, light in a certain amount of time travels a certain distance. And this would be 1 second, right? So my car would be going 10 meters in 1 second, in a sense. You could say, instead of saying that you're 25 years old or however old you are, you could say, I took 25 trips around the sun. But that makes things really complicated. We really need time, this thing that we kind of invented, to slice it up into, smaller and smaller pieces so that we can understand, this motion. Okay? It just makes everything easier for us to understand. Now, when you think of energy in the sense of is this some particle? How does a particle contain energy, like a photon? You could try to look at a photon as, say, like this orb or this sphere. And it's pulsing. In other words, like a balloon, you kind of squish it in and it makes this shape, and then you kind of go the other way, so it returns to its normal shape, and then it gets squished in this way, right? And you could say it's kind of pulsing or oscillating or, vibrating in such a way. This would be, your high and your low of your frequency, right? So your light wave, if you will, is kind of like this pulsating orb you know, as it's traveling. But that's not correct. You know, there's no membrane to a photon. You know, it doesn't have a shape that we know of. We just say that it's, you know, quantized. It's this energy pushed down into this almost infinitely small point in space and time, and it's this ripple of the membrane, this four-dimensional membrane that is space-time. Another way you could try to, and you know, I'm sure you're familiar with the Newton's cradle. If you view it as like you see a particle over here and you can see that particle later over here, and you say, well, what is that? What is it when it's in here? What is that? Is it any one of these ball bearings in our Newton's cradle at any given point, or is it just that wave of energy being carried through all of them? And then what you see in the end result, what you sense, what you detect on your detection material when you detect a photon, right? But again, you know, this isn't very accurate. It's not the best, you know, image of what's going on, and unfortunately, we just don't have a good, you know, image. We just have to kind of rely on what the mathematics and the experiments show us. Okay. You know, these localized vibrations, if you will. So, if you've seen this before, I'm sure you've seen. So people try to explain how gravity works, and you've seen what looks like this trampoline, basically, and you take this bowling ball and you drop it on you place it on your trampoline, and that trampoline warps, it curves in, and then they take another ball and they say, oh look, you know, see how it falls down. You know, that's how gravity works, right? The mass warps this fabric. But you know, in this case, you're using a three-dimensional sphere and putting it on this two-dimensional fabric, and space-time is four-dimensional. But then you're also using the gravity of the Earth to explain gravity in this situation. But the other thing too is, I mean, the only reason this fabric is warping the way it is with this ball is because the fabric is being stretched. It's pulling in the opposite direction. Now, does space-time have, you know, edges to it that are being pulled on and stretched? Possibly. But we really just kind of refer to it more as everything's pulling on everything else, in a way. You've probably seen another example, and maybe a slightly better example of, you know, this fabric that is space-time, right? I'm just trying to draw this out in the sense of, I guess this would be a cubic lattice, if you will. And you'll see these pictures where they say, oh, well, you put your matter in there and it warps space-time. And it pulls and stretches this fabric. And that's more accurate to what's happening, right? But again, here you have these edges, you know, of your lattice that are being pulled on. And you know, whatever your lattice is made of, it's not like space-time is made up of that stuff. So if this were, you know, some string or some type of yarn, right? You know, space-time isn't made up of string or yarn, unless you count string theory. But anyway, you know, anti-gravity. In the case of the trampoline, right? You could just say anti-gravity is this bowling ball just being pushed up from underneath, right? And so as you try to roll something on it, it just gets pushed off and rolled off the trampoline, right? Anti-gravity in this case would just be kind of like this ball of yarn in the middle that's unraveling, and your whole lattice is expanding out as that ball of yarn in the middle is unraveling. Okay? So that's really kind of what we're trying to define when we talk about anti-gravity. Unification theory can account for anti-gravity if it needed to. But if you were to say if it were a particle, that's kind of what we're going on, right? To give this image, we'll draw our protons, and before, when we talked about, substance A plus B gives you what? Well, B doesn't have to be a substance. It can be just the changes you made to A. Maybe it was just, temperature differential, or the structure, that has changed. So maybe you need a specific alignment of a structure, to have some type of behavior that gives us some weird thing that we've never seen before. If we say this is our electron cloud, and when you think of electron orbiting, does it really orbit? Its energy is kind of more, spread out around, kind of like this, as one, wave, moving about. It's hard to tell, I guess. So anyway, if you say your mystery substance, whatever it is, would have some weird behavior, something we've never seen before, and let's just say this is trying to, decay in a sense. And you say this for some reason this cloud of electrons is saying, no, I'm not going to let that happen. So this never really gets its chance to fully, emit, if you will. And it's just kind of sitting in here wobbling about and just releasing this unknown, particle or amount of energy in a way that acts like our space-time, in a sense, expanding. That's kind of what you would hope for. And the effects of something like this, in a sense, this isn't real. Nobody's witnessed this. But it's not to say that it's completely impossible that can't happen. It's just saying that in your search, if you were looking for something like that, who knows? Maybe you need some special, element or what have you, maybe some antimatter version of some element that's just behaving something like this. It's breaking down and only releasing energy in the form of its space-time constituents, if you will, if that's even a thing, right? We don't know, but and that would be kind of like this anti-gravity, if you would, pushing out from your substance. So anyway, that's it. Anti-Gravity Explained Part 2. This is the end. I'm Professor K. Thank you.